This is our second lesson from the gases unit. This is more information using the ideal gas law, but also looking into gas stoichiometry, or how we can use conversion factors in the context of a chemical reaction to solve gas type problems. So you'll be able to use molar relationships and reactions to perform gas law calculations. We'll also talk about density of gas calculations as well. So this question, why does the pressure of a gas increase with an increase in temperature? So you need to be able to explain the particle behaviors here. If you increase the temperature, you're increasing the average kinetic energy of the particles, so you're increasing the frequency and force of the collisions between the molecules and the walls of their container, which is pressure. This value, the molar volume of an ideal gas at STP, this is 22.42 liters. This is on your reference sheet. So any gas at STP will occupy, any 1 mole of any gas at STP will occupy 22.4 approximately liters of volume. So the way that number is derived is from the ideal gas law. So we have that PV equals nRT. If we want to get volume by itself, you divide by pressure. And what you would do here, since this is at STP, you would input standard temperature and pressure values, and you would input the value for R that you're dealing with atmospheres here, so the 0.8206, and we're dealing with 1 mole of a gas, so N is 1. That's where you get the 22.4. So here's an example similar to what we were doing the other day. A sample of oxygen gas has a volume of 2.5 liters at STP. How many grams of oxygen are present? So what we can do here is use the ideal gas law. It says it's at STP, so we know the temperature is 273.15. We know the pressure is 1 atmosphere. We can just use the atmosphere value for that, so we can use the 0.08206 value for R. You could use 760 torr if you want, which means you'd have to use the 62.36 value for R. So now you substitute in and solve. So the pressure is standard pressure, 1 atmosphere. The volume is 2.5 liters. We're going to solve for N here, number of moles. We have R, which is 0.08206, and we have the temperature, which is 273.15. When you solve for N, your number of moles, you get 0.111 moles of oxygen. It's asking you for grams of oxygen, so that's just a simple moles to gram conversion, and you get the 3.57 grams. This next example, you would be given an equation for this, so we'll work through it. Quicklime is produced by the thermal decomposition of calcium carbonate. Calculate the volume of CO2 at STP produced from the decomposition of 152 grams of calcium carbonate. So we have, here's the calcium carbonate, and again, you'd be given this equation. Here's the quicklime, here's the CO2. This is already balanced. So we can just run this as a stoichiometry problem. So we have 152 grams of calcium carbonate. Let's convert that to moles. The molar mass of calcium carbonate is approximately 100 grams per mole. CO3. And now we want to figure out volume of carbon dioxide. So we would go to moles of carbon dioxide, 1 mole of CO2, 1 mole of calcium carbonate. That's from the equation. And now it's asking us for the volume at STP. Because the volume is at STP, we can go right to that 22.42 liters of CO2 per mole of CO2 to get our answer. The other way that you could do this is you could stop here. You could get moles of CO2, which happens to be 1.52 moles. And you could substitute that into PV equals nRT. Pressure would be 1 atmosphere. Volume is what we're looking for. Number of moles is our 1.52. R would be your 0.08206. And temperature would be standard temperature, the 273. So if you substitute in that way and solve, you're still going to get that same answer as before. If the problem is not at STP, you have to use the ideal gas law eventually. So number 3, a sample of methane gas, again, equation would be given, having a volume of 2.8 liters. Let me just put this up here. Blah, 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 mixed with oxygen gas. The mixture was unignited, so we're doing a combustion reaction between methane and oxygen. But again, you'd be given the balanced equation. You wouldn't have to do the equation and then solve the problem. Calculate the volume of CO2 formed at a pressure of 2.5 atmospheres and a temperature of 125. So there's several things involved here. This is a limiting reagent problem because you're given the quantities of methane and the quantity of oxygen, so you have to figure out which one's going to run out first. So we're going to do PV equals nRT for methane, and then also for our other reactant, oxygen. So our methane is 1.65 atmospheres, our volume is 2.8 liters, moles is what we're looking for, R is 0.08206, temperature 25 degrees Celsius is 298. When we solve for moles, we get 0.189 moles of methane. Do the same thing for oxygen, 1.25 times 35 liters equals N times 0.08206 times 304. Again, I'm using this value for R because I'm dealing with atmospheres as my pressure unit. If I'm dealing with torr, I have to use the other one. When I solve for N here, I get 1.75 moles of oxygen. So now I have to figure out which one is the limiting reagent by taking them both to CO2. So moles of CO2 would be 1 mole CO2 because that's the coefficient, 1 mole of methane, so mathematically I'm good, that's 0.189 moles of CO2 possible with that amount of methane. For the oxygen, I'd have 1 mole CO2, 2 moles of oxygen, there's my coefficient, so that is 0.875 moles of CO2 possible with that amount of oxygen they have. So because that quantity, the possible quantity of CO2 is so much lower, that means that my methane is going to run out first. So that's the number of moles of CO2 I'm actually able to make. Now I can substitute that back into PV equals nRT. Pressure is 2.5 for the carbon dioxide. The volume is my unknown. The moles is 0.189. R is 0.08206. Temperature is 398 Kelvin, and that volume would be 2.47 liters. Oh, this is just the same thing repeated. Oh, and there's our answer. Okay, next example, we have another decomposition reaction. We have potassium chlorate decomposing into potassium chloride and oxygen. Again, you do not have to be able to predict this. You would be given the equation. So we have 50 grams of potassium chlorate decomposing and producing oxygen gas, but we're not at STP, so we can't go right to volume. We have to use PV equals nRT here. So 50 grams of potassium chlorate, the molar mass of potassium chlorate is about 122.45 grams. Now I can take that to moles of oxygen, 3 moles of oxygen for every 2 moles of potassium chlorate that decompose. That gives me 0.612 moles of oxygen are forming. Now I have to substitute that into PV equals nRT. Pressure is 0.93 atmospheres. Volume is my unknown. Moles is 0.612. R is 0.08206. Temperature is 37 degrees Celsius, which is 310. So volume is 16.7 liters. Now the next thing I'm going to show you how to calculate, and this is not on your reference sheet. You can derive it using information on your reference sheet, which is a pain in the butt, but it's possible. Or you could just memorize this equation I'm going to give you. You can calculate the molar mass of a gas if you have the density, or vice versa. If you have the density, you can calculate its molar mass. Now here's all these different calculations that wrap together. So we have PV equals nRT. We have density equals mass over volume. So here's volume they have in common. The number of moles is equal to the mass divided by the gram formula mass. So you can put all these together and rearrange it to get to this final equation, which is a huge pain in the butt if you don't want to deal with that whole, interaction of all these equations. So in my opinion, I think you should just memorize this. Molar mass, dirty P. So molar mass is dRT over P. D is density. R is your gas constant, T temperature, P pressure, and molar mass there. So the way the units would work out is shown here. Here's your density unit for gas is grams per liter. Here's your unit for R. Here's your temperature unit. Here's your pressure unit. So when everything cancels out, you're left with grams per mole, which is the unit for molar mass. So if you remember this equation, it'll be super helpful. Molar, it's one of the very few that I would remember. That and combined gas law. So what's the density of fluorine gas at STP? So molar mass equals dRT over P. Molar mass of F2 is about 38 grams per mole. So there's your molar mass. Density is what we're solving for. R is 0.08206. Temperature is, we're going to do 273.15 because it's at STP. And pressure is 1 atmosphere. And I'm using the 1 again because I'm using that 0.08206 value. So when I solve for density, I get 1.70 grams per liter. It's like magic, only not. Here's another one. The density of the gas was measured at 1.5 atmospheres and 27 degrees Celsius and found to be 1.95 grams per liter. Calculate the molar mass of the gas. So these are pretty straightforward questions. Any greater, if you went through this method of solving it, would be fine with that. Let me see here. Okay, so molar mass is what we're solving for. Density is 1.95, R 0.08206. Temperature 27 degrees Celsius is 300 Kelvin, and pressure is 1.5 atmospheres. When you solve for X, you get about 32 grams per mole. What diatomic gas would this be? Question. Okay, so that's about it for this little stretch of calculations. We'll work on some more practice problems in class.